Good evening, guys. So, this lecture we're going to study about Feynman diagrams. Next slide, please. Yeah. So first, let us give an analogy or sort of a motivation towards Feynman diagram. So, we all know what a circuit is, right? So let's consider this illustration of a circuit. So this is not an actual circuit. This is just for illustration to explain the different parts. So clearly, you can see an AC voltage source, a resistor, a capacitor, and an inductor. They represent different functions for the voltage across the element in terms of charge flowing through the element. So essentially, what this is saying is we can find the voltage through any element just by looking at it. Like for example, if the capacitance of the the resistance of the resistor is R, we can find out what the voltage is which is flowing through the resistor. And similarly for the capacitor and the inductor. Next slide, please. So if Q is the total current in the system, so these are the equations that relate the voltage across capacitor, resistor, and inductor respectively with the current. So yeah, next slide, please. So we can encode even more details into this circuit, like energy conservation, energy and charge conservation. For this, we have the Kirchhoff rule. The first rule basically says that the charge flowing into a vertex or a node is equal to the charge flowing out of it. So I is equal to I1 plus I2, like that. The second rule is an identical statement, but for energy. The consequence of this is that the net voltage around any closed loop is in a circuit is zero. So using these two rules, now we know that we need to encode similar instructions into a diagram for particle physics. So let's see how we do that. Next slide, please. So a diagram for particle physics um, should have these three points basically. So it should have distinguishable representation of different elements. Elements meaning the different particles and how they interact. So it should conserve relativistic energy and momentum, and it should explain what happens at vertices. And since we're dealing with particles with different spins, angular momentum should also be conserved. Next slide, please. So let's take an example. Consider the electron and positron colliding will annihilate and produce a muon and anti-muon pair. Since the electron and muon are electrically charged, the simplest way through which they interact is through electromagnetism. We all know that the force carrier for electromagnetic force is a photon. So we can say that they interact through an exchange of photon. In these, the photon is called the propagator and is usually represented by a wavy line. So as you can see in the bottom of this page, we have represented the simplest way these two can interact in using a Feynman diagram. Now Ashwin will tell you how to, he'll explain the different components of the diagram and how to formulate an equation for the collision using this diagram. Ashwin.
Thank you, Raguveer. Next slide. Uh, Before starting into Feynman diagram, I would like to give an introduction to what the Feynman diagram is. First, let's compare it with organic chemistry. In organic chemistry, let's take any compound like ethanol, famous compound, ethanol. Every line and every dot and every letter has a separate meaning, right? Like that, in Feynman diagram, every point has a meaning. We can also compare it with electronics, because every diagram represents something. Resistor, conductor, it represents something. Here, every line and every dots represents something. Okay, without any further ado, let's start into components of the Feynman diagram. External lines. And external lines are the particles that come in and out in the initial state and final state. It is the ingoing and outgoing momenta. Vertex factor, but for each vertex, that is where ABC meet, has a factor. It determines the order of the diagram. Now we will see about yeah, ABC, which is the single order function, and we will also look into two vertex function, which is the higher order functions. Internal lines. Factors for internal particles exchange between vertices only applies to particles internal to the diagram. I will show you what internal line is next slide. Momentum conservation at the vertex. At each vertex, we are enforcing for momentum conservation. we will include a factor known as IG. Talk about that later. And integrals over the internal momentum. We are integrating over the internal momentum alone. We are not calculating the external lines. For only for internal lines, we will do an integral to to tell that momentum and energy function. Next slide. Here you can see what's the external lines and what are the internal lines are. What is the vertex? Left side one is a single order Feynman diagram. Right side is the second order Feynman diagram. I will pause here for like about 10 seconds and you can observe what the internal line and external lines are because it will be very very important. Next slide. Okay. Feynman rules. Every book and every author interprets the Feynman rules in different way. I referred Griffiths and one lecture from University of Toronto, and I have I made it easier. Like it is the same as Feynman rule, but the number of steps varies. I combined some steps and I added some steps to understand Feynman diagram more easily. Okay, for the step one of my Feynman rule is notation and coupling constant. Notation is the labeling the incoming and outgoing for momenta. We label the internal momenta as P, and we will label the internal momenta as Q, and we will label the external momenta as P. We put an arrow on each line to keep track of the positive direction. For each vertex, we write down a factor of minus Ig. G is called the coupling factor. Here in toy model, G has the dimension of momentum, but when we are taking the real world examples like going outside of toy theory, like we find that G normally has G is a dimensionless quantity. Okay, here let's see about the three diagrams. The leftmost is the diagram which is mentioned in Griffith. It is a single order. The other two are higher order, and both have two vertex. Uh, though uh, the coupling factor, the factor is minus Ig square. Okay. Next slide. Propagator. For each internal line. For first diagram, we don't have internal line, but for the next two, we have internal line. For each of those internal line, we add a propagator of the value I by q square minus mb square c square. We have to notice that q is the internal momenta, but the q should not be equal to minus q should not be equal to minus mb square c square, because then the equation will go haywire. So q should not be equal to mb square c square, and mb square is the mass of the particle p and c is the speed of light. For the propagator, here it represents the expectation value. It gives the probability for finding the particle. Okay, next slide. Step 3, energy and momentum conservation. When I mentioned this term and components for Feynman rules, I will tell it again. For each vertex, we write a delta function. Delta function is nothing but like a function, like f of x is a function, right? Same like that, delta is a function of the form 2 pi power 4 del 4 k1 plus k2 plus k3, where k are the 3 4 momenta coming into the vertex. If the arrow leads outward, the value of k is minus. If the arrow leads inwards, then it is plus. We can see here at the bottom the equation P1 is plus, but P2 and P3 are minus because the arrow goes outward. Uh, for uh, for the next two diagrams, we are having two vertex, right? So we are having two delta functions, one delta function for each vertex. I will just pause here for like 5 seconds. You can just see the equation, the diagram. Next slide, Ra. Now let's integrate over the internal momenta. For each internal line, we write down a factor of integral 1 by 2 pi to the power 4 and d4q. Let's add this function to the formula. We get these equations. I will pause here for some time so you can see the equations. We are just adding the factor, we are just multiplying the factor one by one. So at the last we will do the integration and we will also remove some factors and we will get the value what we need. Okay, next slide. Now we are integrating, we are performing the integral and also we are eliminating one of the delta terms. We had two del power 4 terms, right? So we are removing one del 4 term and we are performing the integral and we get this beautiful equation. I will wait and you can see the equations and let's move on. Okay, next slide. The result will include a delta function. We had a delta function, right? 2 pi 4 del 4 p1 plus p2 to p3 p4, right? We erase this factor, and if we erase this factor, what remains im? We need the value of m. We are interpreting the Feynman diagram to find the value of m because m is the amplitude function from which we can calculate the decay rate and lifetime of a particular particle. For first one, for ABC toy theory, the value will be m is equal to g. G m is a dimensionless. M is a dimensionless quantity where g, first we mentioned g has a dimension of momentum, right? But in the real world examples, the g has dimensionless. Here for the first term, g will be dimensionless. Okay, I will now hand over to Raguveer who will summarize all the Feynman rules and he will tell you very shortly.
Thank you, Amal. Please. So to summarize what Ashwin was talking about, the Feynman diagrams are, and hey, 1 second, sorry, the Feynman diagrams and their construction from the Feynman rules are central tools for analyzing particle physics processes. And let's summarize what Ashwin just told. So, first we need to identify the external and internal particles and draw arrows to represent the positive direction. Positive direction is the positive direction of time. So, the external particles are particles that have an on-shell solution, which means that they are real particles. They can be measured. The internal, I mean, they can be detected. Internal particles have off-shell solution, which means they are virtual particles, like the photon, the propagator that we consider. It is a virtual particle, which means it doesn't exist long enough for us to detect anyway. So next we connect the particles to the propagator. So this is, yeah. So that's very simple. Next, we include a delta function at each vertex to conserve the momentum, energy, and momentum. So, if you remember from last lecture, we discussed what a delta function is. So, it's just like any function, but if you input any quantity other than zero, the function will go to zero. So, if the input is zero, so if energy and momentum are conserved, the delta function will be one. If they are not conserved, it will go to zero. So that's basically it. So then we add a factor of integration of 1 by 2 pi power 4 to d4q for each internal line present, and then we cancel the delta function. Cancelling meaning if the energy and momentum are conserved, then we replace delta function with a one. That's what cancelling is, and then we solve the equation to get the probability amplitude. That's all. Next slide, please. Caveat emptor. This is just a Latin phrase which means buyer beware. Which means that if you're buying a product from a shop, you the buyer is responsible for the quality of the product. How does this represent Feynman diagram? How does this tie into Feynman diagrams? Let's see. Feynman diagrams are useful mathematical tools, but as a physical description of scattering process, they should be interpreted with care, and this is why. So all these collisions happening in the quantum realm, which is probabilistic by nature. So two particles can interact in any number of ways. The more number of outcomes, the more Feynman diagrams. The Feynman diagrams are not very accurate for more number of outcomes. So in the case of electron-muon scattering, they interact through an exchange of photons. Consider that example because it is the simplest way they can interact. So then when there are constraints on the final state that restricts particle energies or angles of collision, the Feynman diagrams are no longer an accurate representation of the process. And lastly, as you've already guessed, the Feynman diagram doesn't exhibit any time evolution. It doesn't tell us how the particle evolves. It is just a representation of wave function overlap of the initial state and the final state with the final state. Next slide, please. So, while the Feynman diagram is a very elegant way to represent the equations involved, but owing to the sheer magnitude of possible outcomes, it is not very efficient. For higher order interactions, the Feynman diagrams give but an effective description. For such cases, we can use an amplitude hadron shown below, which is a step ahead. The amplitude hadron is a solid that we construct. So when you solve the area of the amplitude hadron, you get a simplified equation for what we just saw. So that's all. Thank you.